Okay, let's say if we look at solving by using series methods, various differential equations, and we'll say we have, as an example, we can look at solving for y whenever y prime minus 2y is equal to 0. The tutors section, and to initiate, we can go into new worksheet, and then go into the tools section, go down to tutors, and some older versions of Maple might have assistance instead. And we have in the menu, you can go down to differential equations and into the ODE analyzer. And we want to plug in y prime minus 2y is equal to 0. And for what we have in this table that appears, we're going to go into edit and then assist. And we have insert derivative of y with respect to x, and this will be of first order, and then you insert, and then click done, and we're going to have minus 2, not just 2y, but minus 2 times, and not just y, but y of x is equal to 0. And once you're done typing, you click on add. So you have dy over dx minus 2 times y of x is equal to 0. And click done, and you have the equation to appear. And then we have solving symbolically. And instead of the default method, okay, we're going to go with the formal series and solving, and we have this particular display. Okay, now looking at what we have for the solution, if I put this in the context of getting out of the gamma notation and putting it in the context of the summation concerning factorials, okay, and right now we have 2 to the n times x to the n, and I can compile this together as 2x raised to the n. And keeping in mind, now we have with gamma of n plus 1, that is equal to n times gamma of n, and this will be equal to n factorial. And we can say that for the first constant, we'll just let this be at c0, but you can keep the c1 as it is. So we have in the rewrite, okay, so we have with y of x, okay, so we'll say we have c0, and we have times the summation as n goes from 0 to infinity. And we have of 2 times x quantity to the n, and gamma of n plus 1 is equal to n factorial. So this will be your summation solution, and the summation is going to correspond to the factor or the function e raised to the 2x, and that will be the display of the results for what we have in the function e to the 2x as well as its summation counterpart. Now let's say we have a third order differential equation where we have the third order derivative of y plus 9 times the first order derivative of y is equal to 0. And if I put this in the context of Maple, again we have going back to tutors, differential equations, ODE analyzer, we have edit, and we have assist, and we have insert the derivative of y with respect to x of third order, and then we're going to have plus 9 times the first order derivative. So we go back to assist, so you have y with respect to x of order 1, insert, and then we have equal to 0, then we add. So this is what we have now. Click on Done, solve symbolically. Again, going with the formal series and looking at solving, and this is what we have on display. Okay, so we will have on display, we'll just say that C0 is going to represent C1, and we will say that for C1 we'll have that to represent C2. Now for what we have within the summation, we have -9 to the n times x to the 2n plus 1 all over gamma of 2n plus 2, and just sort of extracting what we have here. So we have -1 to the n times 9 to the n times x to the 2n plus 1, and for the gamma of 2n plus 2, okay, this would be equivalent to what we have for 2n times the gamma of 2n plus 1, and just spreading out what we have here. Now we have -1 to the n. Now for 9 to the n, I'm going to put this in terms of base 3. So we have 3 raised to the 2n times x raised to the 2n plus 1 degree. And for 2n times the gamma of 2n plus 1, okay, this is going to go to 2n plus 1 factorial. And to put the 3 raised to the 2n in the context of the 2n plus 1 degree, I'm going to factor out 1/3. So we have 1/3 times -1 to the n times 3 raised to the 2n plus 1 times x raised to the 2n plus 1 all over 2n plus 1 factorial and just compiling together. So you have 1/3, you have -1 to the n, and I can put together the bases 3 and x and say we have 3x raised to the 2n plus 1 degree all over the factorial of 2n plus 1. And as for what we have for the remaining item, okay, now we have C of 3, and we'll just let that be C of 2. And for the bases, now we have -9 to the n times x to the 2n, and we have all over gamma of 2n plus 1. And writing in terms of base 3, okay, so you have -1 to the n, and we have 9 to the n. We'll go ahead and write this as 3 to the 2n degree, and we have times x to the 2n, and for gamma of 2n plus 1, okay, so just rolling back, and this would go to 2n factorial, and squeezing together what we have here, we have -1 to the n times 3x raised to the 2n all over the factorial of 2n. So for what we have in the context of taking what we have for y of x, so we're going to have C0 and we have plus C1 and this will be times the summation as n goes from 0 to infinity. Okay. And we have, in fact, you have 1/3, and so I can move the 1/3 in front of the C1. And here we have -1 to the n times 3x raised to the 2n plus 1 all over 2n plus 1 factorial. And then we have for the subsequent term, so you have C of 2, and you have times the summation as n goes from 0 to infinity. Again, we have -1 to the n, and we have times 3x quantity raised to the 2n all over 2n factorial. Okay, and let me mention, okay, from this particular part, you see we have minus C2, but again, you have C0 minus C2, and the difference between constants is still going to be a constant. So I'm just going to cluster what we have together. So you have C0 minus C2. So we'll just regard this as a constant. So I'll just leave this as C0. And 1/3 of C1, 1/3 of a constant, is still going to be a constant. And for -1 to the n times 3x to the 2n plus 1 all over 2n plus 1 factorial. Okay, now for this particular result, okay, this is going to be in correspondence to the sine function, where we're going to have the sine of 3x. And then we have with C of 2 for -1 to the n times the quantity of 3x to the 2n over 2n factorial. Okay, we're working with the angle at 3x, and the corresponding function we have is going to be cosine. So we have, in the case of what we have for both the general solution and the summation. Okay, so just sort of sifting through what we have here. So again, we have y of x. Difference between constants is still a constant. And 1/3 of a constant is still going to be a constant. And one more time. So you can write your summation solution in this particular context, and for what we have for the functions in explicit form, still general, we have y of x equal to C0 plus C1 sine of 3x plus C2 times the cosine of 3x. Okay, now let's say if I have solving the third order differential equation, instead of y triple prime plus 9y prime is equal to 0, let's say if I make this into a different statement. And if we look at solving through the use of Maple, and again through the ODE Analyzer Assistant. Okay, so if I edit, assist, okay, so again I have y with respect to x of third order, insert, done, we have minus 9 times. We have y with respect to x of first degree, insert, done, and we have equal to 0. And if I add, so this is the equation we're looking at. Click on Done. Solve symbolically, and utilizing formal series and solving. So this is the display that we have at the moment. Okay, so for what we have in this statement, what I'm going to do here, I'm going to make this C1 into a C0. And again, just have C1 to represent C of 2. And for what we have in the statements, okay, so you have 9 to the n, x to the 2n plus 1. And we have all over gamma of 2n plus 2. Okay, so and taking what we have at the moment, okay, is that we're going to have in this particular layout, okay, so we have for 9 to the n. If I put this in terms of base 3, so you have 3 squared to the n, and this is going to be 3 raised to the 2n degree. And if I put this in the context of what we have in the framework, okay, whereupon we have matching up with the 2n plus 1 degree. So 3 to the 2n, this would be 1/3 of 3 raised to the 2n plus 1 degree. And for what I have in the numerator, okay, so 9 to the n times x to the 2n plus 1. You get from 9 to the n, so we have 1/3 times 3 to the 2n plus 1, and have times x to the 2n plus 1. And if I cluster together the bases, 3 and x, so we have 1/3 of 3x raised to the 2n plus 1. And for the gamma function, now we have for the gamma of 2n plus 2. So this would be like the gamma 2n plus 1 plus 1. So you would have like 2n plus 1 times the gamma of 2n plus 1. And in factorial terms, okay, this would be just 2n plus 1 factorial. So for what we have in terms of the summation, okay, so you have n going from 0 to infinity, 9 to the n times x to the 2n plus 1. Okay, what's going to happen here? Okay, so you have 9 to the n, x to the 2n plus 1. So you have, and I'm going to put the 1/3 on the outside. And you have 3x raised to the 2n plus 1. And we have in the denominator. Okay, so we have 2n plus 1 factorial. Now, in the case of what we have with C of 3, so I'm just going to say that, okay, C of 3, we have C of 2 is equal to C of 3. And for what we have for this particular summation, okay, so you have, again, so you have 9 to the n, and that's going to be equal to 3 raised to the 2n. And notice this time we had the base x in this summation to be raised to the 2n degree. So if I take 9 to the n times x to the 2n, we have 3 to the 2n times x to the 2n. And if I put together, we have 3x raised to the 2n. And for the gamma of 2n plus 1, again, you would have 2n times the gamma of 2n, or succinctly, okay, if I roll back by 1, you'll be taking the factorial of this. So gamma of 2n plus 1, it's going to be the factorial of 2n plus 1 minus 1. So this will go to 2n factorial. And so we're going to have in the summation, for the summation part, okay, so I have n going from 0 to infinity. And we have the top part, so we have 3x to the 2n. We have all over 2n factorial. And so we have in the summations, okay, so we have for y of x, okay, so we have c naught. And so we have 1/3 of c1 times the summation as n goes from 0 to infinity. We have 3x to the 2n plus 1 all over 2n plus 1 factorial, and we have plus c2 put in place of c of 3. We have times the summation again as n goes from 0 to infinity of 3x raised to the 2n over 2n factorial. And you got that minus, okay, so just say we have minus c2. And if I take what I have and put all together, okay, so we have with c naught minus c2, difference between constants is still going to be a constant. And 1/3 of a constant is still going to be a constant, so I'll just rewrite this. Okay, so you have c of 1. We have times the summation as n goes from 0 to infinity. And we have of 3x raised to the 2n plus 1 all over 2n plus 1 factorial. And we have plus, again, c2 times the summation as n goes from 0 to infinity. And we have of 3x raised to the 2n all over 2n factorial. So this is our summation solution, and translating what we have and putting in the context of our function. So we have a constant. Now we have c1, and for 3x raised to the 2n plus 1 degree over 2n plus 1 factorial. Okay, this will be what we have in the case of the hyperbolic sine of 3x. And we have, for the summation as n goes from 0 to infinity, so if you have a base of the 2n all over the factorial of 2n, this is going to be mapped with the hyperbolic cosine function, and we'll be taking the hyperbolic cosine of 3x. And so what we have all together, okay, we have the summation solution as well as the functional solution, and that is the result.